250 million years ago, Earth looked very different from the world we know today. Almost all the continents were joined together to form one enormous landmass called Pangea. Vast forests, wide deserts and long rivers stretched across this giant supercontinent, creating many different environments. It was during this time that dinosaurs first appeared, grew and spread across the land. As millions of years passed, Pangea slowly broke apart, changing the climate, the oceans and the routes that animals could travel. These changes affected where dinosaurs lived, how they evolved, and how different groups became separated from one another. The Earth before Pangea was very different from the world we know today. The continents that exist now had not yet formed in their present shapes or locations. The oceans were also arranged in ways that would seem strange to anyone looking at a modern map. During the earliest part of Earth's history, the surface of the planet changed again and again over extremely long periods of time. Huge pieces of the Earth's outer shell slowly moved across the surface. They sometimes came together to form large landmasses, and at other times broke apart into smaller continents. These movements took place so slowly that they could not be noticed within a human lifetime. Instead, they happened over millions of years through natural geological processes. Earth itself formed about 4,540 million years ago, from dust, rock, and gas left behind after the birth of the Sun. During its earliest years, the young planet was extremely hot. Its surface was covered with flowing molten rock. Powerful volcanic eruptions were common, and large objects from space struck the surface very often. These impacts released enormous amounts of energy and kept the young Earth hot for a long time. As the planet slowly cooled, the outer layer hardened into solid rock. This hard outer layer became the beginning of the Earth's crust. The crust was not one unbroken shell. Over time, it cracked into many large and small sections known today as tectonic plates. These plates floated on top of a deeper layer of hot rock that moved very slowly. Heat from deep inside the Earth caused this movement. As the hot rock below shifted, it carried the plates along with it. This process continued year after year, century after century, and for billions of years. It is still happening today. The earliest crust was very different from the crust that exists now. Much of it was thin and unstable. New rock formed as molten material rose from deep inside the Earth. Older rock was pushed downward into the planet, where it melted again. This continuous cycle slowly changed the size and shape of the continents. Some early pieces of crust disappeared completely, while others survived and became the oldest parts of the continents that still exist today. Scientists have found ancient rocks in places such as parts of Africa, Australia, Canada, Greenland, India, and South America that are more than 3 billion years old. These rocks provide important clues about the Earth's earliest history. They show that some areas of continental crust became stable very early. These ancient pieces of crust are called cratons. Cratons formed the strong foundations of future continents. Although the continents later broke apart and joined together many times, many cratons remained in existence throughout these changes. During the early history of the Earth, there may have been several small continents instead of a few large ones. These early landmasses slowly grew as volcanic activity created new rock and as smaller pieces joined together through collisions. Every collision added more material to the growing continents. Mountains formed where these land masses crashed into one another. Wind, rain, rivers, and ice slowly wore down these mountains. The broken rock was carried into nearby seas, where it collected in thick layers. Over time, these layers hardened into new sedimentary rocks. The oceans of the ancient Earth also changed constantly. Water likely reached the Earth's surface through volcanic gases and from icy objects that struck the planet during its early history. As the Earth cooled enough for water to remain in liquid form, rain fell over enormous periods of time. Water collected in low areas and formed the first oceans. These oceans covered much of the planet. They played an important part in cooling the Earth's surface and creating conditions that allowed life to appear. The earliest oceans were different from today's oceans. Their temperatures were often much warmer. Their chemical makeup also changed over time. Minerals dissolved from rocks entered the water through rivers and volcanic activity. These minerals slowly changed the composition of seawater. The oceans also contained much less oxygen than they do today. This made them very different environments for living organisms. Life first appeared in these ancient oceans. The earliest known living things were tiny single-celled organisms. They lived in shallow seas where sunlight could reach the water. Some of these organisms gained energy from chemicals found in the water, while others eventually developed the ability to use sunlight through photosynthesis. This process released oxygen into the environment. At first, the oxygen produced by these tiny organisms did not remain in the atmosphere. Instead, it reacted with iron dissolved in seawater. This reaction created layers of iron-rich rock that can still be found today. Only after much of the dissolved iron had combined with oxygen did oxygen begin to collect in the atmosphere. This important event changed the Earth's environment and allowed more complex forms of life to develop much later. As the continents slowly moved across the Earth's surface, they sometimes came together into larger groups. These groups were not permanent. The forces inside the Earth continued to move them. Large oceans opened as continents drifted apart. Later, those oceans closed again when continents moved back towards each other. This repeating pattern became one of the most important features of Earth's geological history. Scientists believe that several supercontinents existed long before Pangea formed. A supercontinent is a huge landmass made from most or nearly all of the Earth's continental crust joined together. These supercontinents formed through the movement of tectonic plates. They remained together for millions of years before breaking apart again. One of the earliest proposed supercontinents is called Valbara. Scientists believe it may have existed more than 3 billion years ago. Evidence for Valbara comes from similarities found in ancient rocks in parts of southern Africa and Western Australia. These rocks have similar ages and geological features. Some scientists believe this suggests they were once connected. However, because the rocks are extremely old and have changed greatly over time, there is still discussion about whether Valbara truly existed as a single supercontinent. Another early proposed supercontinent is called Ur. Scientists believe Ur formed more than 3 billion years ago. Unlike later supercontinents, Ur may not have included most of Earth's land. Instead, it may have been one of the earliest stable continental areas that survived for an exceptionally long time. Parts of what became Africa, Australia, India, and Antarctica may have once belonged to Ur. After Ur, scientists have suggested the existence of another large landmass known as Keenorland. This supercontinent may have formed about 2,700 million years ago. It likely included large parts of what are now North America, Greenland, Scandinavia, Africa, Australia, and other regions. Powerful geological forces later pulled Keenorland apart. New oceans opened between the separating landmasses, changing the appearance of the Earth once again. The breaking apart of Knorrland affected volcanic activity around the world. As the continents separated, magma rose through cracks in the crust and formed new ocean floors. Volcanoes released gases into the atmosphere. These gases influenced the climate over very long periods. The movement of the continents also changed ocean currents, which affected temperatures in different parts of the world. During these ancient times, the Earth experienced several periods of widespread cooling. Ice spread across large areas of the planet during some of these times. Scientists have discovered evidence of ancient glaciers in rocks that are now found in warm regions. This tells researchers that the continents were once located in very different places. As tectonic plates carried them across the globe, regions that had once been covered by ice later moved closer to the equator. One of the greatest changes in Earth's history happened when oxygen levels increased in the atmosphere. This event took place about 2,400 million years ago. Oxygen produced by tiny living organisms gradually built up in the air. Many early forms of life that could not survive in oxygen-rich environments disappeared. Other organisms adapted and evolved. The growing amount of oxygen made it possible for more advanced forms of life to develop over long periods. As time passed, another proposed supercontinent, known as Columbia, formed. Some scientists also call it Nuna. It may have existed about 1,800 million years ago. Columbia included many of the Earth's continental blocks, joined into one enormous landmass. Large mountain ranges formed where continents collided. Rivers carried rock from these mountains into surrounding seas, creating thick layers of sediment. Columbia remained together for hundreds of millions of years before beginning to break apart. Large cracks appeared in the crust as heat built up beneath the supercontinent. Magma pushed upward and weakened the landmass. Eventually, the continents separated and new oceans formed between them. This process happened very slowly over many millions of years. After Columbia came another supercontinent called Rodinia. Rodinia formed about 1,100 million years ago. It became one of the largest landmasses in Earth's history before Pangea. Scientists have gathered evidence for Rodinia by studying ancient rocks, mountain belts, and magnetic minerals preserved inside rocks. These clues help researchers estimate where the continents were located long ago. Rodinia was surrounded by a vast ocean. The arrangement of land and sea influenced climate around the world. Ocean currents carried heat across the planet. Winds followed changing patterns as they moved across the land and sea. Rainfall differed from place to place. Dry regions developed in some areas, while other regions received large amounts of rain. The interior of Rodinia may have been dry because it lay far from the oceans. Coastal areas likely received more rainfall. Rivers flowed across the land, carrying sand, mud, and gravel into nearby seas. These sediments slowly built up in thick layers that later hardened into rock. During the time of Rodinia, simple forms of life continued to evolve in the oceans. Tiny organisms remained the most common living things on Earth. Some larger soft-bodied organisms also began to appear toward the later part of this period. They lived mostly in shallow marine environments where conditions supported life. Rodinia eventually began to break apart because of movements inside the Earth. Hot material beneath the crust weakened the supercontinent. Cracks formed and the land slowly separated into smaller continents. As new oceans opened, the shape of the Earth changed once again. The breakup of Rodinia may have contributed to major changes in climate. Some scientists believe the Earth entered extremely cold periods during this time. Ice sheets spread across large parts of the planet. Some researchers suggest that nearly all of Earth's surface may have been covered by ice during certain times. Although scientists continue to study this idea, there is strong evidence that glaciers reached regions much closer to the equator than they do today. Volcanic activity continued even during these cold periods. Volcanoes released gases into the atmosphere, including carbon dioxide. Over long periods, these gases may have helped warm the planet enough for the ice to melt. As temperatures increased, rivers carried nutrients into the oceans. These nutrients supported the growth of living organisms. Following the breakup of Rodinia, another proposed supercontinent called Pangea formed. Pangea existed for only a relatively short period before breaking apart again. It formed about 600 million years ago. The continent soon separated into several large landmasses. These movements prepared the way for the later formation of Pangea. During the time after Pangea, the oceans became home to increasing numbers of living organisms. Many new forms of life appeared during what scientists call the Cambrian explosion. Animals with shells, hard body parts, and many different body shapes became much more common. The fossil record from this time shows an enormous increase in the variety of life. The continents continued to move throughout this period. Some drifted toward the equator, while others moved toward the poles. Their changing positions influenced temperatures, rainfall, and ocean circulation. Different environments developed across the planet. Some areas became shallow tropical seas filled with marine life. Other regions became dry deserts or cold environments. The ancient oceans before Pangea were not always the same oceans. They opened and closed as continents moved. One ocean might disappear completely while another formed elsewhere. Ocean floors were constantly created at underwater ridges where magma rose to the surface. Older ocean floors slowly sank back into the Earth's interior at deep ocean trenches. Because ocean floor is continually recycled, very little of the oldest ocean crust still exists today. Continental crust behaves differently. It is generally thicker and lighter than oceanic crust. Because of this, it usually survives much longer. This is one reason scientists can still study ancient continental rocks, even though almost all ancient ocean floors have disappeared. Scientists have learned about these ancient continents by studying rocks from around the world. They examine the age of rocks using radioactive elements trapped inside minerals. These elements change into other elements at known rates over long periods. By measuring these changes, scientists can estimate how old a rock is. This method has revealed the ages of many ancient rocks and helped build the timeline of Earth's history. Magnetic minerals inside rocks also provide valuable information. When molten rock cools, tiny magnetic minerals line up with the Earth's magnetic field. These minerals preserve the direction of the magnetic field at the time the rock formed. By studying these magnetic records, scientists can estimate where continents were located long ago and how they moved over time. Mountain ranges also provide important clues. When continents collide, rocks become folded, broken, and pushed upward. Even after mountains are worn down by erosion, the rocks preserve signs of the ancient collision. Scientists can match similar mountain belts found on different continents. These matches suggest that the continents were once joined together, before later drifting apart. Fossils help scientists understand the history of ancient continents as well. Similar fossils found on different continents can show that those lands were once connected or located much closer together. Before the oceans separated them, plants and animals could spread across connected land areas. Later, as continents drifted apart, their descendants evolved separately. Ancient climate records preserved in rocks also reveal the movement of continents. Coal deposits, xenomime, indicate areas that were once covered by rich forests. Coral fossils show where warm, shallow seas once existed. Glacial scratches carved into rocks reveal where ancient ice sheets moved across the land. Desert sandstones show places that were once dry and windy. By studying these clues together, scientists can reconstruct ancient maps of the Earth. Volcanoes played a major role throughout Earth's history before Pangea. They created new land, released gases into the atmosphere, and built islands in the oceans. Some volcanic islands eventually collided with continents, adding new rock to their edges. This process gradually increased the size of continents over hundreds of millions of years. Earthquakes also shaped the ancient world. As tectonic plates moved, stress built up along their boundaries. When the stress became too great, rocks suddenly broke, releasing energy as earthquakes. These events occurred throughout Earth's history and continue today. The atmosphere before Pangea changed many times. Early air contained very little oxygen and much more carbon dioxide, water vapor, methane, and other gases than today's atmosphere. Over time, photosynthetic organisms increased oxygen levels. This change affected climate, weather, and the evolution of life. The atmosphere continued to develop as volcanic activity, biological processes, and geological changes interacted over immense spans of time. Rain, rivers, wind, waves, and ice constantly reshaped the land. Mountains slowly wore away through erosion. Rivers carried sediments into lakes and oceans. New rocks formed from these sediments. Deep inside the Earth, heat and pressure transformed existing rocks into new forms. Some rocks melted completely and later cooled into new igneous rocks. These ongoing processes created the rock cycle, which has operated throughout Earth's history. The continents before Pangea were never fixed in one place. Their movement was steady, although extremely slow. A continent might travel thousands of kilometers over hundreds of millions of years. During these journeys, it experienced changing climates as it crossed different parts of the Earth. Areas that were once near the equator later reached colder regions, while areas once covered by glaciers later became warm tropical environments. The ancient Earth before Pangea was a world of continuous geological activity. Continents formed, joined together, broke apart, and drifted across the planet. Oceans expanded and disappeared. Mountains rose and were worn down. Volcanoes built new land, while earthquakes reshaped old landscapes. Tiny living organisms slowly changed the atmosphere and prepared the planet for increasingly complex life. These long and gradual changes laid the geological foundation for the later formation of Pangea, which would eventually unite most of Earth's land into a single enormous supercontinent. The Earth has changed many times during its very long history. The continents that people know today have not always been in the same places. They have slowly moved across the surface of the planet over an extremely long period. Mountains have risen, oceans have opened, and seas have disappeared. Land has broken apart and later joined together again. These changes happened so slowly that no human could ever notice them during a lifetime. Scientists learned about these changes by carefully studying rocks, fossils, mountains, earthquakes, volcanoes, the ocean floor, and the movement of the Earth's crust. Long before the time of the dinosaurs, the Earth's continents were not separated in the way they are today. They were moving little by little because the outer shell of the Earth is divided into huge pieces called tectonic plates. These plates float on a hotter and softer layer of rock that lies deeper inside the Earth. Heat from the Earth's interior causes this softer rock to move very slowly. As it moves, it carries the tectonic plates along with it. This movement is usually only a few centimeters each year, but over many millions of years, it changes the shape of the world. The formation of Pangea was one of the greatest events in the Earth's geological history. Pangea was a giant supercontinent, made up of almost all the Earth's major land areas, joined together into one enormous body of land. It did not appear suddenly. Its formation took a very long time. Many older continents and smaller land areas slowly moved toward one another until they finally became connected. Before Pangea existed, the Earth had several ancient continents that were separated by wide oceans. These ancient continents had their own mountain ranges, rivers, forests, deserts, and coastlines. Each continent continued to move because of the steady movement of tectonic plates beneath it. As time passed, the oceans between many of these landmasses became smaller. The distance between the continents slowly decreased as they drifted toward each other. One of the most important ancient continents was Gondwana. Gondwana was made up of land that would later become Africa, South America, Antarctica, Australia, the Indian subcontinent, and several smaller pieces of land. Gondwana existed for a very long time before Pangea formed. During its history, it experienced many changes in climate. Some parts were covered with forests, while others were covered with glaciers during colder periods. Evidence of these ancient glaciers can still be seen in rocks found across several modern continents that were once connected within Gondwana. Another major continent was Laurentia. This ancient land later became the main part of North America. Laurentia was surrounded by oceans and separated from Gondwana by a large stretch of water. Over a long period, Laurentia slowly moved because of the forces inside the Earth. As it travelled, it came closer to other continents. Baltica was another ancient continent. It contained land that later became much of northern Europe. Siberia was another separate continent that later became much of northern Asia. Smaller pieces of land also existed between these larger continents. These smaller landmasses moved in different directions and often became trapped between larger continents during later collisions. The oceans between these ancient continents did not remain the same forever. Ocean floors were constantly changing. New ocean crust formed at long underwater mountain chains where melted rock rose from deep inside the Earth. At the same time, older ocean crust slowly sank back into the Earth's interior along deep ocean trenches. This process is called subduction. As ocean crust disappeared beneath continents or beneath other ocean plates, the oceans slowly became narrower. As the oceans grew smaller, the continents came closer together. Eventually, the edges of some continents met. When two continents collided, neither one easily sank beneath the other, because continental crust is lighter than oceanic crust. Instead, the edges of both continents were pushed upward. Thick layers of rock folded, cracked, and rose to form giant mountain ranges. These mountain-building events happened many times during the formation of Pangea. Each collision created new mountain chains, while older mountains slowly wore away through erosion caused by wind, rain, rivers, ice, and changes in temperature. The mountains that formed during these ancient collisions were once much taller than many of the mountains seen today. Over hundreds of millions of years, erosion reduced their height. One important stage in the formation of Pangea happened when Laurentia and Baltica moved toward each other. The ocean between them slowly closed as oceanic crust disappeared beneath the Earth's surface. Eventually, these continents collided. Their collision created large mountain ranges and united separate pieces of land into a larger continent. Another important event involved Avalonia, which was a smaller continent located between larger landmasses. Avalonia slowly drifted toward Laurentia and Baltica. After a long period, it collided with them and became attached. This made the growing landmass even larger. Farther south, Gondwana also continued moving. The movement was extremely slow but steady. The gap between Gondwana and the northern continents gradually became smaller. Ocean crust continued sinking into the Earth's interior, bringing the continents closer together over many millions of years. As Gondwana approached the northern landmasses, island chains, volcanic arcs, and smaller continents became caught between them. Some of these smaller pieces were pushed onto the edges of larger continents instead of sinking into the Earth. Their rocks became part of the growing continental crust. Today, geologists can identify these ancient fragments by studying differences in rock types, fossils, and mineral compositions. Eventually, Gondwana collided with the northern continents. This was one of the most important moments in Earth's geological history. The collision completed the formation of Pangea. Nearly all of the Earth's major land areas became joined together into one vast supercontinent that stretched across much of the planet. The joining of these continents created mountain ranges that extended for thousands of kilometers. Some of today's mountain systems contain rocks that formed during these ancient collisions. Even though erosion has greatly changed their appearance, scientists can still trace their origins back to the time when Pangea formed. The collision of continents also caused the Earth's crust to become thicker in many places. Huge amounts of pressure changed existing rocks deep underground. Heat and pressure transformed many rocks into new forms through a process known as metamorphism. Minerals inside the rocks changed, crystals grew larger, and entirely new rock types developed. At the same time, melted rock from deep inside the Earth rose into the crust. Some of this magma cooled beneath the surface to form large bodies of igneous rock. In other places, volcanoes erupted, adding fresh layers of lava and ash. These volcanic activities also became part of the growing supercontinent. The formation of Pangea greatly changed the shape of the world's oceans. As the continents joined together, many smaller oceans closed completely. One enormous ocean surrounded the outside of Pangea. This giant ocean is known as Panthalassa. It covered most of the Earth's surface and was much larger than any ocean that exists today. Another important body of water remained along the eastern side of Pangea. This was the Tethys Ocean. It separated parts of Gondwana from some northern regions, before later geological changes altered its size and shape. Over time, the Tethys Ocean also changed, as continents continued moving. The position of Pangea affected weather and climate across the planet. Because so much land was joined together, areas far from the coast received much less moisture from the oceans. Rain often fell near the coast, but much less reached the center of the supercontinent. Large dry regions developed across many inland areas. Some parts of Pangea experienced seasonal rainfall while others remained dry for long periods. Rivers crossed many regions before reaching the sea. Large lakes formed in some low areas. Wind carried dust across dry lands, leaving behind thick layers of sediment that later hardened into rock. The coastlines of Pangea were very long and faced different directions. Coastal climates varied depending on their location. Some regions received frequent rainfall, while others experienced long dry seasons. Warm, shallow seas covered certain low coastal areas during times when sea levels were higher. Plants spread across much of the supercontinent. Different plant groups adapted to different climates. Forests covered regions that received enough rainfall. Other plants became adapted to dry conditions. Plant remains collected in swamps and wetlands later became buried beneath layers of sediment. Over very long periods, heat and pressure transformed some of this buried plant material into coal. animals also spread across Pangea. Since many continents were connected, many species could move across large areas without crossing wide oceans. This allowed some animal groups to spread over enormous distances. Fossils of similar animals have been found on continents that are now separated by oceans because those continents were once joined together. Scientists discovered many clues showing that today's continents were once connected. One clue comes from fossils. Fossils of the same ancient plants and animals have been found in rocks on continents that are now thousands of kilometers apart. These animals could not have crossed the wide oceans that exist today. Their fossils make sense only if the continents were once connected. Another clue comes from rocks. Mountain ranges on one continent often match mountain ranges on another continent when the continents are placed back together. The rocks have similar ages, minerals and structures. This suggests they were once parts of the same mountain system before the continents separated. The coastlines of some continents also appear to fit together. The eastern coastline of South America closely matches the western coastline of Africa. Scientists do not rely only on the shape of the coastlines because coastlines change over time, but the matching rocks, fossils and geological structures provide much stronger evidence that these continents were once joined. Ancient climate records provide more evidence. Rocks formed by glaciers have been found in areas that are now warm. Other rocks formed in tropical conditions are found in places that are now much colder. These discoveries show that continents have moved across different climate zones during Earth's history. Magnetic minerals inside ancient rocks also help scientists understand continental movement. When melted rock cools, tiny magnetic minerals line up with the Earth's magnetic field at that time. These minerals preserve a record of the direction toward the magnetic poles. By studying many rocks of different ages, scientists can determine how continents moved over very long periods. The ocean floor has also provided important evidence. During the middle of the 20th century, scientists carefully mapped the ocean floor and discovered long underwater mountain ranges where new crust forms. They also found deep trenches where old ocean crust sinks into the earth. These discoveries helped explain how continents move and how supercontinents like Pangea formed. Earthquakes and volcanoes occur mainly along the edges of tectonic plates. These patterns show where plates meet, separate, or slide past one another. By studying these active regions today, scientists better understand the same kinds of processes that slowly brought ancient continents together to form Pangea. The formation of Pangea was not a smooth process. Some continents changed direction several times before finally joining. Ocean basins opened and closed more than once. Some mountain ranges formed, were worn down, and then new mountains formed during later collisions. Geological history contains many repeated cycles of movement and change. The joining of continents also changed ocean currents. As coastlines changed, water flowed along new paths. These changes affected the movement of heat around the planet. Climate patterns slowly changed as a result. Different regions became wetter or drier depending on their location and the new arrangement of land and sea. Sea life also responded to these changes. As oceans closed, some marine habitats disappeared. Other new habitats formed along the coastlines of the growing supercontinent. Marine animals adapted to changing environments, while some species disappeared and others spread into new areas. The Earth's atmosphere was also influenced by these long-term geological changes. Volcanoes released gases into the atmosphere. Plants removed carbon dioxide through photosynthesis and released oxygen. The burial of large amounts of plant material also affected atmospheric composition over long periods. These natural processes continued while Pangea was forming. Rivers flowing across the growing supercontinent carried sand, mud, and gravel from mountains into low areas. Layer after layer of sediment built up in valleys, lakes, and shallow seas. Over time, these sediments hardened into sedimentary rocks that preserve fossils, footprints, and records of ancient environments. Many minerals that people use today formed during geological events connected with continental collisions. Heat, pressure, and underground fluids concentrated valuable minerals into deposits that later became important resources. Gold, copper, iron, and many other minerals were affected by the geological activity that accompanied the formation of Pangea. Scientists continue to study Pangea because it helps explain many features of the modern Earth. Understanding how continents join together helps researchers understand mountain building, earthquakes, volcanoes, mineral resources, fossil distribution, climate history, and the movement of tectonic plates. Each new discovery adds more detail to the story of how the supercontinent formed. Modern technology has greatly improved the study of ancient continents. Satellites measure the present movement of tectonic plates with great accuracy. These measurements show that continents are still moving today. Although the movement is very slow, it confirms that the same natural processes responsible for forming Pangea continue to operate. Computer models allow scientists to reconstruct the positions of ancient continents. These models combine information from rocks, fossils, magnetic records, and geological structures. By bringing all this evidence together, scientists can create detailed maps showing how continents gradually approached one another before forming Pangea. Drilling deep into the ocean floor has provided additional information. Samples collected from beneath the seabed contain records of ancient oceans and the movement of tectonic plates. These records help scientists understand when oceans opened, when they closed, and how continental collisions happened. Research continues because many details are still being investigated. Different scientists sometimes suggest slightly different paths for the movement of certain continents or smaller land fragments. New evidence from field studies, laboratory work, and advanced technology continues to improve understanding of how the Earth's landmasses slowly join together. The formation of Pangea remains one of the greatest examples of the Earth's continuous geological activity. The slow movement of tectonic plates brought together ancient continents that had once been separated by wide oceans. Ocean crust sank into the Earth's interior, continents collided, mountain ranges rose, volcanic activity reshaped the crust, and nearly all of the Earth's major land areas became united into one immense supercontinent through natural processes that unfolded over hundreds of millions of years. Life on Earth during the time before the dinosaurs was very different from the world that people know today. The land looked different, the climate was different, and the living things that covered the land and filled the seas belonged to groups that no longer exist or that later changed into very different forms. During this period, almost all of Earth's land was joined together into one enormous landmass called Pangea. This giant continent stretched across a large part of the planet and was surrounded by one huge ocean. The shape of the land affected the movement of air, the flow of water, the amount of rain that different places received, and the kinds of living things that could survive in different areas. Long before the first dinosaur appeared, life had already spent hundreds of millions of years changing and becoming more diverse. The first simple forms of life had appeared in the oceans long before animals lived on land. Over an extremely long time, living things slowly changed through natural processes. New kinds of organisms appeared while others disappeared forever. By the time Pangea had formed, the Earth already had forests, rivers, lakes, insects, fish, amphibians, and many kinds of reptiles. The land was full of life, although it looked very different from the forests and grasslands that exist today. The earliest forests on Pangea were made up of plants that were unlike many of the trees people see now. Flowering plants did not yet exist. There were no fields filled with colourful flowers and no fruit trees growing naturally across the land. Instead, forests contained giant club mosses, horsetails, seed ferns, tree ferns, conifers, cycads, ginkgos, and many other ancient plants. Some grew very tall and formed thick forests that stretched across large areas where enough rain fell. Others grew in drier places where they had adapted to survive with less water. The climate across Pangea was not the same everywhere. Some regions were warm and wet throughout much of the year. Thick forests covered these places and supported many different kinds of animals. Other regions received very little rain. Large dry areas stretched across the center of the continent because moisture from the surrounding ocean often could not reach these distant inland regions. Rivers in these dry places sometimes became smaller during long periods without rain, and many plants had to survive difficult conditions before wetter seasons returned. Large rivers crossed many parts of Pangea. They carried water from mountains toward lakes and the great ocean that surrounded the continent. These rivers moved sand, mud, and small rocks from higher ground into lower areas. Floods sometimes covered wide regions, leaving behind rich layers of soil where many plants could grow. Wetlands formed beside rivers, creating homes for fish, amphibians, insects, and many other forms of life. Lakes were also common across different parts of the continent. Some lakes remained full throughout the year, while others became much smaller during dry seasons. Animals often gathered near these water sources because they provided drinking water and supported many kinds of plants. Fish swam through these freshwater environments, while insects flew above the surface and laid their eggs in quiet pools. Amphibians spent much of their lives near these waters because their eggs needed moist conditions to survive. The skies above Pangea were filled with insects. Insects had already become one of the most successful groups of animals on Earth. Many kinds of beetles, dragonflies, cockroaches, mayflies, and other insects lived among the forests and wetlands. Some fed on leaves, wood, or dead plants. Others hunted smaller insects. Many insects played an important part in breaking down dead plants and animals, helping nutrients return to the soil where new plants could grow. Spiders, scorpions, millipedes, and many other small animals also lived across the forests and the forest floor. Fallen leaves, broken branches, and rotting wood created countless hiding places for these creatures. They fed on insects, dead plants, fungi, and other small organisms. Together they formed an important part of the natural system that kept forests healthy over long periods. Fungi were common throughout the forests of Pangea. Although they are often overlooked, fungi performed an important job by breaking down dead trees, fallen leaves, and the remains of animals. Without fungi, dead material would have built up across the forests for much longer periods. Instead, nutrients returned to the ground, allowing fresh plants to continue growing year after year. The soils of Pangea supported many tiny forms of life that could not be seen without special equipment that did not exist at that time. Bacteria and other microscopic organisms lived in the soil, in water, and even inside other living things. These tiny organisms helped recycle nutrients and supported the growth of plants. Even though they were invisible to the animals living around them, they were essential for keeping ecosystems functioning. amphibians remained among the most important animals living on land during much of this period. Their ancestors had been the first vertebrate animals to move from water onto land many millions of years earlier. Even though amphibians had become successful land animals, they still depended on water for reproduction because their eggs dried out easily. This meant they often stayed close to rivers, lakes, ponds and wetlands where moisture remained available. Some amphibians grew to very large sizes. They had broad heads, powerful jaws, and strong bodies that allowed them to hunt fish and smaller animals. Many spent much of their time waiting quietly in shallow water before quickly catching prey that came within reach. Others searched through wet forests for insects, worms, and smaller animals hidden beneath leaves or inside soft soil. Reptiles gradually became more successful across many parts of Pangea because they were better adapted to life away from water. One of their greatest advantages was the development of eggs protected by strong outer coverings. These eggs could survive on land without drying out as quickly as amphibian eggs. This allowed reptiles to spread into many environments that amphibians found difficult to occupy. Many different reptile groups appeared during this time. Some remained small and fed mainly on insects. Others became much larger and hunted other animals. Some developed strong teeth for eating tough plants. Different species filled different roles within their environments, helping create a rich variety of life across the continent. Among these reptiles were the synapsids, a group that included many animals which were distant relatives of mammals. Some synapsids looked very different from modern mammals, yet they shared certain features that later became important in mammal evolution. Some species had powerful jaws with different kinds of teeth that allowed them to cut and crush food more efficiently. Others developed body structures that helped them move effectively across different kinds of land. Plant-eating synapsids spent much of their time feeding on leaves, stems, seeds, and other plant material. Their strong teeth and jaws allowed them to process tough vegetation that many other animals could not easily digest. Large herds of these animals may have moved across certain regions in search of fresh food and reliable water sources. Meat-eating synapsids hunted many smaller animals. Their sharp teeth allowed them to catch prey, while strong muscles helped them overpower struggling animals. Hunting required patience, quick movement, and good senses. These predators helped keep animal populations balanced by removing weaker or slower individuals. Many animals protected themselves in different ways. Some had thick skin, others developed large body sizes that made attacks more difficult. Some relied on speed while others remained hidden among plants or inside burrows until danger had passed. Many small animals stayed active during cooler parts of the day to avoid larger predators. Burrowing became an important survival strategy for many species. Underground tunnels protected animals from extreme heat, cold nights, predators, and dry conditions. These burrows also provided safe places for laying eggs and raising young. During long dry seasons, some animals remained underground for extended periods until better conditions returned. The climate of Pangea changed over time. Some years brought more rainfall while others were much drier. Longer climate changes lasting thousands or even millions of years also affected forests, rivers, lakes, and deserts. As environments changed, living things either adapted, moved into new areas, or disappeared. Evolution continued shaping life generation after generation, slowly producing new species that were better suited to changing conditions. Volcanic activity influenced life in many regions. Volcanoes released lava, ash, and gases into the atmosphere. Fresh volcanic rock slowly broke down into new soil that plants could eventually colonize. Large eruptions sometimes damaged nearby forests and forced animals to move into safer regions. Over long periods, new ecosystems developed as plants and animals returned to affected areas. Earthquakes also occurred as the huge landmass experienced movements deep within the planet. Rivers sometimes changed direction, lakes formed or disappeared, and mountain ranges slowly rose higher. These geological changes created new habitats while removing others, encouraging further changes in the plants and animals living across the continent. The mountains of Pangea influenced rainfall and temperatures. Moist air released rain on some mountain slopes, while other areas remained much drier. Different plant communities developed depending on the amount of available water. Higher elevations often supported different species than nearby lowlands because temperatures and growing conditions varied. The coastline surrounding Pangea supported many different forms of life. Shallow coastal waters contained shellfish, early sharks, many kinds of fish, and countless smaller marine organisms. Tides regularly covered and uncovered coastal areas, creating habitats for animals that could survive changing water levels. Some reptiles and amphibians visited these coastal regions to hunt or reproduce. Farther from shore, the Great Ocean contained an enormous variety of life. Coral reefs supported many marine animals, while deeper waters contained fish, cephalopods, and other creatures that had adapted to darker environments. Marine ecosystems continued changing as new species appeared and older groups disappeared. Life on land and in the sea remained connected in many ways. Rivers carried nutrients into the ocean, supporting marine life near the coast. Dead marine organisms sometimes washed onto beaches, providing food for scavengers. Birds did not yet dominate the skies, but insects moved between water and land throughout their life cycles, linking freshwater and terrestrial ecosystems. Even before the dinosaurs appeared, Earth already supported rich and complex communities of living things. Every forest, river, lake, wetland, coastline, and desert contained countless interactions between plants, animals, fungi, and microscopic organisms. These living communities continued changing as the environment changed, preparing the stage for the many new groups of animals that would later appear across Pangea. Long before the first dinosaurs appeared, the supercontinent known as Pangea stretched across a huge part of the Earth's surface. It was the largest landmass that had existed for a very long time, bringing together areas that are now spread across many different continents. Because so much land was joined into one enormous body, the climate and the landscapes were very different from those of the modern world. The arrangement of the land changed how air moved through the atmosphere, how rain fell, how rivers flowed, and how living things spread across the land. Every part of Pangea experienced the effects of its great size, although conditions were not the same everywhere. The outer edges of the supercontinent lay next to vast oceans. These coastal regions often received more moisture than places farther inland, because winds blowing from the sea carried water into the air. Clouds formed more easily near the coasts, and rain fell more often in many of these areas. Rivers carried fresh water across the land before emptying into the oceans. Plants were able to grow in many coastal regions because the soil received enough moisture to support forests, ferns, seed plants, and many other forms of vegetation that had already evolved during earlier periods of Earth's history. The center of Pangea was very different. Since it was so far from the oceans, much less moisture reached these inland regions. Many winds lost most of their water before reaching the heart of the supercontinent. As a result, large areas remained dry for long periods. Rain could become rare, and many rivers disappeared before reaching the sea. Lakes sometimes shrank during long dry seasons, leaving behind thick layers of salt and minerals after the water evaporated. These dry conditions shaped the plants and animals that were able to survive there. Temperatures across Pangea could change greatly during different times of the year. In many inland regions, the land heated up strongly during the warmer months because there was little nearby ocean water to reduce the heat. During cooler months, temperatures could fall sharply. This created strong seasonal changes over much of the supercontinent. Living things had to survive both hot and cooler conditions as the seasons changed. Near the equator, sunlight remained strong throughout the year. These regions often stayed warm, although rainfall varied from place to place. Some equatorial areas received enough rain to support thick forests filled with tall plants, giant ferns, horsetails, seed ferns, and early conifer trees. Other equatorial regions remained much drier, because changing wind patterns prevented regular rainfall. The result was a mixture of green landscapes and dry open areas, spread across different parts of the same latitude. Farther away from the equator, the climate became more seasonal. Summers could become very warm, while winters became much cooler. Rainfall often depended on changing wind directions during different seasons. Some years brought enough rain to fill rivers and lakes, while other years were much drier. These changes affected the growth of plants and influenced where animals searched for food and water. The southern parts of Pangea included lands that had once been covered by enormous ice sheets during much earlier times. Long before the supercontinent reached its greatest size, glaciers had spread across parts of the southern continents. As the Earth's climate slowly became warmer, many of these glaciers melted away. They left behind valleys, rocky surfaces marked by moving ice, and large deposits of gravel, sand, and other materials carried by the glaciers. These ancient signs remained part of the landscape long after the ice disappeared. Mountains formed in several regions where ancient continents had collided during the creation of Pangea. When huge pieces of the Earth's crust pushed against one another, the rocks slowly folded, cracked, and rose upward over millions of years. These mountain ranges stretched across great distances. Some reached heights much greater than many mountains standing today because they had only recently formed and had not yet been worn down by erosion. Wind, rain, rivers, and changing temperatures slowly began breaking these mountains into smaller rocks, carrying sediment into nearby valleys and basins. Large river systems developed across many parts of the supercontinent. Rain falling in mountains flowed downhill, through streams that joined together into larger rivers. These rivers carried sand, mud, and small stones across wide plains. During times of heavy rainfall, rivers sometimes overflowed their banks, spreading fresh layers of sediment over nearby land. These sediments helped create fertile areas where plants could grow more easily. Some rivers crossed hundreds of miles before reaching the sea, while others ended in inland lakes or shallow basins where the water gradually disappeared through evaporation. As the water vanished, minerals remained behind, creating thick deposits that would later become part of the rock record. Scientists study these rocks today to understand the changing climate of the supercontinent. Floodplains developed beside many rivers. During wet seasons, water spread across these flat lands, leaving behind fresh mud rich in minerals. Plants quickly grew in these areas whenever enough moisture remained. Fallen leaves, branches, and dead plants collected in swamps and wetlands. Over very long periods, some of this plant material became buried beneath layers of sediment. Heat and pressure, acting over millions of years, eventually changed some of these buried remains into coal. Not every part of Pangea contained forests. Large open regions covered by hardy plants stretched across dry landscapes where rainfall remained limited. Some plants developed thick leaves or protective outer coverings that helped reduce water loss. Others produced seeds able to survive dry conditions until rain returned. These plant communities formed the main food source for many plant-eating animals living in these regions. The coastlines of Pangea were extremely long and varied greatly from one place to another. Some coasts contained sandy beaches where waves slowly shaped the land. Other coastlines had rocky cliffs created by ancient geological activity. River mouths formed broad deltas where fresh water mixed with seawater. Sediment carried by rivers built new land along these coastal areas as layer after layer settled onto the seabed. Shallow seas covered some low-lying regions near the edges of the continent. These warm waters supported many kinds of marine life. Shellfish, corals, fish, and many other sea creatures lived in these coastal waters. Their remains later became buried beneath sediments, forming rocks that preserve valuable fossils today. Powerful storms sometimes struck coastal regions. Strong winds, heavy rain, and large waves reshaped beaches and river mouths. Floodwaters spread across nearby plains, carrying mud and broken plant material into lakes and shallow seas. These events became part of the natural cycle that constantly changed the appearance of the land. The interior deserts of Pangea covered enormous areas. Strong sunlight, limited rainfall, and dry winds created harsh conditions for life. Sand dunes formed where steady winds carried loose sand across the surface. These dunes slowly shifted. As the wind changed direction over time, some reached great heights and stretched across large parts of the landscape. The patterns left behind by these ancient dunes are still preserved in many sandstone formations found on different continents today. Dust storms were likely common in some dry regions. Fine particles of soil and sand were lifted into the air by strong winds and carried over long distances. These storms changed the surface of the land by removing loose material from some places and depositing it elsewhere. Dust also settled into lakes and rivers, becoming mixed with other sediments. Many valleys formed between mountain ranges. Rivers flowing through these valleys carried water from higher ground toward lower areas. Valleys often supported richer plant life because water collected there more easily. Animals searching for food and fresh water gathered around these regions, especially during dry seasons. Large lakes appeared in different parts of Pangea. Some existed for long periods, while others expanded and shrank depending on seasonal rainfall. Fish, amphibians, and many small water animals lived in these lakes. Plants grew along the shorelines, providing shelter for insects and other small creatures. When lakes dried up, they left behind layers of mud that later hardened into rock. Wetlands developed wherever water remained close to the surface for long periods. Thick vegetation covered these low areas. Fallen plants accumulated in waterlogged ground, where decay happened slowly because little oxygen reached the buried material. Over immense spans of time, repeated burial created thick deposits of organic matter. The soil across Pangea varied greatly depending on local conditions. In wetter regions, rich soils supported dense plant growth. In dry regions, thin soils contained less organic material because fewer plants grew there. Floods, volcanic activity, weathering of rocks, and changing river systems constantly created new soils while removing older ones. Volcanic activity occurred in several parts of the supercontinent. Molten rock sometimes reached the surface through cracks in the Earth's crust. Lava spread across the land before cooling into solid rock. Volcanic ash settled over nearby areas, adding minerals to the soil after long periods of weathering. These eruptions also released gases into the atmosphere. influencing climate over different lengths of time. Earthquakes occasionally shook regions where the Earth's crust remained active. The movement of large rock plates created fractures and faults beneath the surface. Some earthquakes triggered landslides in mountainous areas, sending huge amounts of rock into valleys below. Rivers often changed course after such events, creating new channels across the landscape. The sky above Pangea also reflected its changing climate. Dry regions often experienced clear skies for long periods, allowing strong sunlight to heat the ground during the day. At night, temperatures could fall quickly because there were few clouds to trap heat near the surface. Wetter regions saw more frequent cloud cover and regular rainfall as moist air rose and cooled. Seasonal winds influenced many parts of the supercontinent. As temperatures changed between land and sea, air moved across vast distances. Some seasons brought moist air inland, increasing rainfall. Other seasons brought dry air that reduced cloud formation. These yearly patterns affected rivers, lakes, forests, and the movement of living creatures across the land. The climate of Pangea did not remain exactly the same throughout its long existence. Over millions of years, gradual changes in the Earth's orbit, volcanic activity, mountain building, and the slow movement of tectonic plates influenced temperatures and rainfall. Some regions became wetter, while others became drier. Forests expanded during favorable periods and retreated when conditions became harsher. The landscapes continued to change as rivers shifted, mountains eroded, coastlines moved, and new sediment covered old surfaces. Around 245 million years ago, during the Middle Triassic period, the first true dinosaurs appeared on Earth. They did not suddenly spread across the land or become the largest animals alive. Their beginning was quiet and gradual. They were part of a much larger group of reptiles that had been changing over millions of years. These early dinosaurs lived in a world that had already experienced great destruction. Before they appeared, the Earth had gone through the largest known mass extinction in its history. This event happened at the end of the Permian period and caused the disappearance of most living species in the oceans and on land. Many habitats became empty, and surviving animals slowly spread into these places. Over many millions of years, new groups of plants and animals developed, including the first dinosaurs. At that time, nearly all of the Earth's land was joined together in one giant supercontinent called Pangea. Since the land was connected, animals could move across very large areas without crossing wide oceans. Rivers, dry plains, forests, valleys, and seasonal wetlands stretched across different parts of this huge landmass. The climate was often hot, and many regions received only limited rainfall during much of the year. Long dry seasons were common, although some areas also experienced periods of heavy rain. These changing conditions influenced the kinds of plants that grew and the animals that survived. The plant life of the Triassic period looked very different from many modern forests. Flowering plants had not yet appeared. Forests were filled with tall conifers, seed ferns, cycads, ginkgo-like trees, and many kinds of ferns growing beneath them. Mosses and other small plants covered moist ground near rivers and lakes. In dry regions, plants had to survive long periods without much water. These plants provided food for many plant-eating animals and shelter for smaller creatures. The earliest dinosaurs shared the land with many other reptiles. They were not the only successful animals of their time. Large amphibians still lived in lakes and rivers. Crocodile relatives known as pseudosuchians walked across the land, and some of them grew much larger than the early dinosaurs. Other reptiles filled many different roles in nature. Some hunted small animals, while others ate plants or insects. The ancestors of mammals were also present. These early mammal relatives were usually small and often active during the night, feeding on insects and other tiny animals. The first dinosaurs belonged to a larger group of reptiles called dinosaurs because of several special features in their bodies. One of the most important differences was the way their legs were placed. Instead of spreading outward from the sides of the body like many reptiles, their legs stood more directly beneath them. This body shape helped support their weight and allowed them to move with greater balance and efficiency. Their hips, legs, ankles, and feet also showed important changes that made walking and running easier. Their bones became lighter while remaining strong enough to support active movement. Scientists believe that dinosaurs evolved from earlier reptiles known as dinosauriforms. These animals already had several features that later became common in true dinosaurs. Over many generations, small changes appeared through natural selection. Animals with helpful features survived more often and produced young that inherited those traits. Slowly, new species developed. There was no single day when the first dinosaur suddenly appeared. Instead, many small changes accumulated over millions of years until these animals became different enough to be recognized as true dinosaurs. The oldest known dinosaurs were generally much smaller than the famous giants that lived much later. Many early species were about the size of a dog, a turkey, or a small deer. Some were only a little larger than a chicken. Their lighter bodies helped them move quickly across the land. Speed allowed them to catch prey, escape danger, and search for food over wide areas. Their smaller size also meant they needed less food than larger animals. One of the earliest known dinosaurs is Eoraptor. Fossils of this animal were discovered in rocks that formed during the late Triassic period in what is now Argentina. Eoraptor was a small, lightly built dinosaur that walked on two legs. It had long hind legs, shorter front legs, a flexible neck, and a long tail that helped with balance. Its hands had fingers with curved claws that could grasp objects or catch prey. Its teeth suggest that it probably ate small animals, insects, and perhaps some plant material as well. Scientists continue to study its fossils because they provide valuable information about the earliest stages of dinosaur evolution. Another important early dinosaur was Herrerasaurus. This animal also lived in what is now Argentina, during the late Triassic period. Herrerasaurus was larger than Eoraptor and measured several meters in length. It had powerful hind legs, sharp claws, and many pointed teeth designed for eating meat. Its skull was long and contained strong jaw muscles that allowed it to bite and hold struggling prey. Although scientists have discussed its exact place in dinosaur evolution, most agree that it represents one of the earliest meat-eating dinosaurs. Another early dinosaur was Staurikosaurus, whose fossils were found in what is now Brazil. This animal had a slim body, long legs, and a lengthy tail. It was also a fast-moving hunter that probably searched for small reptiles, insects, and other animals. Fossils of Staurikosaurus are not complete, but the bones that have been found show many important dinosaur features. These discoveries help scientists understand how dinosaurs spread across different parts of Pangea. Another well-known early dinosaur is Saturnalia. Fossils from Brazil show that this dinosaur was slender and walked mainly on two legs. Scientists believe it belonged to the group that later produced the long-necked giant plant-eaters called sauropods. Saturnalia itself was much smaller than those later giants. It probably ate a mixed diet that included plants and small animals. Its body still showed many early features before the later members of its family became much larger. The fossils of these early dinosaurs show that evolution was already producing different body forms. Some species became better hunters with sharper teeth and longer legs. Others slowly developed bodies that allowed them to eat more plant material. These changes continued over millions of years as new environments appeared and different food sources became available. The study of dinosaur evolution depends mainly on fossils. Fossils form only under special conditions. Most animals die and disappear without leaving any remains behind. Bones are usually broken apart by scavengers, weather, water, and bacteria. In rare cases, an animal is buried quickly beneath mud, sand, volcanic ash, or river sediments. The buried bones slowly become surrounded by minerals carried by underground water. Over a very long time, these minerals replace the original bone tissue, creating fossils that can survive for hundreds of millions of years. Scientists search for fossils in exposed rock layers where ancient sediments have become visible because of erosion. They carefully remove the surrounding rock using small tools to avoid damaging the fossil bones. Every fossil is carefully recorded because its exact position provides important information about its age and the environment in which the animal lived. Laboratories then clean, study, and compare the fossils with those of other species. New discoveries sometimes change earlier ideas about dinosaur evolution because each fossil provides another piece of evidence. The rocks containing the earliest dinosaur fossils are found in several parts of the world, including what are now Argentina, Brazil, Zimbabwe, India, and other regions that were once connected within Pangea. Since these lands were joined together during the Triassic period, animals could spread across great distances. Fossils from different continents often show close relationships because these animals lived before the continents slowly drifted apart. The movement of the continents happened because the Earth's outer shell is divided into large plates that slowly move over time. During the age of the first dinosaurs, the continents had not yet separated into the positions seen today. As millions of years passed, these plates gradually moved apart, carrying dinosaur fossils to different parts of the modern world. Today, scientists discover these fossils on several continents, providing evidence that the land was once connected. The earliest dinosaurs did not immediately become the most common land animals. For many millions of years, they remained only one part of the larger animal community. Many other reptiles were still more numerous and often much larger. The success of dinosaurs increased slowly as environmental changes and later extinction events affected many competing animal groups. Gradually, dinosaurs spread into more habitats and evolved into many new species with different diets, body shapes, and ways of life. The giant supercontinent known as Pangea did not remain whole forever. It existed for many millions of years, but the forces inside the Earth continued to move beneath it throughout that time. The land appeared solid and unchanging to any living creature that walked across it, yet deep below the surface, the planet remained active. Heat from the Earth's interior kept moving through the rocky layers beneath the crust. This heat caused the rocks in the mantle to move very slowly over long periods of time. These slow movements placed stress on the Earth's outer shell. As the stress continued to increase over many millions of years, the great landmass of Pangea slowly began to change. Pangea had formed after many older continents had gradually moved together. The same natural forces that had pushed those continents into one huge landmass did not stop after Pangea was complete. The Earth's crust was still broken into enormous pieces called tectonic plates. These plates rested on the hot and slowly moving rocks of the mantle. They continued to move a very small distance every year. Even though the movement was extremely slow, it never completely stopped. Over millions of years, these small movements became large enough to change the shape of the world's surface. The center of Pangea was far from the oceans. Large parts of the land were dry, because moist air from the seas could not easily reach those distant areas. Rivers flowed across many regions, but many places received little rainfall. Winds carried dust across wide plains. Some regions contained deserts, while others supported forests, wetlands, and river valleys. Plants and animals spread across different environments, and many groups continued to evolve as the climate slowly changed. Deep beneath Pangea, heat continued to rise from the Earth's interior. This heat caused slow circulation inside the mantle. As the hot material rose and cooler material sank, pressure slowly built beneath parts of the crust. The crust could bend, stretch, crack, and slowly become thinner. These changes happened so slowly that they could not be noticed within a human lifetime. They required millions of years before the effects became clear on the surface. One of the earliest signs that Pangea was beginning to separate appeared when long cracks formed across parts of the continent. These cracks are known as rifts. At first they may have appeared as long valleys where the land slowly sank. Earthquakes became more common along these weak zones because the crust was under increasing stress. The rocks slowly pulled apart as the tectonic plates moved in different directions. As the crust stretched farther, molten rock from deep inside the Earth began rising toward the surface through the growing cracks. Some of this molten rock cooled below the ground, while some erupted through volcanoes. These volcanic eruptions covered parts of the land with layers of lava. The lava later cooled into hard volcanic rock. Many separate eruptions happened over very long periods of time, adding more layers as the rifting continued. Scientists have found large areas of volcanic rock that formed during this early stage of the breakup of Pangea. These rocks show that enormous amounts of magma reached the surface while the continent was beginning to split apart. The volcanic activity did not happen in one single event. Instead, it continued through many different periods as the crust slowly weakened and opened wider. The stretching of the crust caused some blocks of land to sink lower than the surrounding areas. Valleys formed between higher ridges. Rivers flowed into these lower regions and carried sand, mud, and gravel. Lakes developed in some of the rift valleys. These lakes collected sediments year after year. Over millions of years, thick layers of sediment built up on their floors. These layers later became sedimentary rocks that preserve evidence of the changing environment. As the rifts widened, seawater eventually entered some of the low areas. A narrow sea formed where solid land had once existed. This marked an important stage in the breakup of Pangea. The new sea slowly grew wider as the tectonic plates continued moving apart. Fresh ocean crust formed between the separating pieces of the continent. Magma rose into the opening, cooled, and became new ocean floor. This process continued again and again as the gap became larger. The first major separation divided Pangea into two enormous landmasses. The northern part became known as Laurasia, while the southern part became known as Gondwana. This separation did not happen suddenly. It developed through millions of years of slow movement. During this time, coastlines gradually changed, rivers found new paths, and mountain ranges experienced new geological forces. Laurasia included lands that would later become North America, Europe, Greenland, and much of Asia. Gondwana contained the lands that would later become South America, Africa, Antarctica, Australia, Madagascar, and the Indian landmass. Although these giant landmasses had separated from each other, they did not remain fixed in place. They continued moving across the surface of the Earth as tectonic activity remained active. The opening ocean between Laurasia and Gondwana slowly became wider. New oceanic crust continued forming along the center of the growing basin. As fresh crust formed, the older crust moved away from the center. This process, called seafloor spreading, steadily increased the distance between the two great landmasses. The movement remained slow, but millions of years allowed the changes to become enormous. The Atlantic Ocean also began its early history during the breakup of Pangea. Long cracks developed between the land that would later become North America and the land that would later become Africa and Europe. These cracks slowly widened until seawater entered them. New ocean floor formed between the separating continents, and the young Atlantic Ocean gradually expanded. The Atlantic Ocean at that early stage looked very different from the ocean seen today. It was much narrower and continued growing over many millions of years. As the ocean widened, the continents on each side slowly drifted farther apart. The coastlines that had once fit closely together gradually became separated by increasing distances of water. Evidence for this ancient connection can still be seen today. The eastern coastline of South America and the western coastline of Africa have shapes that fit together remarkably well. Scientists noticed this long before they fully understood plate tectonics. Later studies of rocks, fossils and mountain ranges provided much stronger evidence that these continents had once been joined as part of Pangea. Many identical fossils have been discovered on continents that are now separated by wide oceans. Fossils of ancient reptiles, plants and freshwater animals appear in rocks of similar ages on different continents. These animals could not have crossed large oceans. Their remains show that the continents were once connected by land before the oceans formed between them. Ancient mountain ranges also provide important evidence. Some mountain belts in eastern North America match mountain ranges found in parts of Europe and Greenland. The rocks share similar ages, structures, and mineral compositions. These mountain systems formed before the continents separated. Later, the opening Atlantic Ocean divided them into different landmasses. The breakup of Pangea also changed the Earth's climate. As new oceans formed, moist air could travel farther into the interiors of the continents. Rainfall patterns slowly changed. Some deserts became smaller, while other dry regions developed in different places. Rivers adjusted to the changing landscapes, and new coastlines created different weather patterns. The changing climate affected plants as well. Forests expanded into some regions, while other plant communities declined. Different species adapted to the new conditions. Seeds spread across fresh landscapes, and flowering plants would later become more important in many ecosystems. Earlier plant groups also continued to grow in many environments during these long geological changes. Animals experienced major changes as the continents separated. Populations that had once lived together gradually became isolated as oceans widened between them. Once separated, different groups evolved independently. Over millions of years, this isolation contributed to the appearance of new species adapted to local environments. Different climates, food sources and habitats influenced the direction of their evolution. Dinosaurs were among the animals living during much of the breakup of Pangea. Early in their history, many dinosaur groups could spread across large connected areas of land. As the continents separated, different dinosaur populations became isolated from one another. New species gradually appeared on different continents as evolution continued through countless generations. The breakup of Pangea also influenced marine life. As new oceans opened, fresh coastlines, shallow seas, and underwater habitats developed. Many marine organisms expanded into these environments. Coral reefs, shellfish, fish, and countless microscopic organisms occupied different parts of the growing oceans. ocean currents also changed as the shapes of the continents continued to shift, affecting the movement of heat and nutrients through the seas. The supercontinent, known as Pangea, was one of the most important stages in the long history of the Earth. During this time, almost all of the planet's land was joined together into one enormous landmass. This period lasted for many millions of years and was filled with constant geological activity. The ground beneath the surface was never completely still. Deep inside the Earth, great amounts of heat moved through the rocky layers, causing the outer shell of the planet to change little by little. These slow changes shaped the surface of Pangea, created mountains, opened cracks in the land, produced volcanoes, and caused earthquakes that affected large areas. The Earth is made up of several layers. At the center is the inner core, which is surrounded by the outer core. Around these is the mantle, a very thick layer made of hot rock that can slowly flow over long periods of time. The outermost layer is the crust, where continents, oceans, mountains, rivers, and valleys are found. Even though the crust feels solid, it is broken into very large pieces called tectonic plates. These plates move very slowly because of the heat rising from deep inside the mantle. The movement is so slow that it cannot be noticed during a human lifetime, but over millions of years it changes the shape of the Earth. Before Pangea formed, many smaller continents moved across the surface of the Earth. These continents slowly came together as the tectonic plates carried them across the planet. Their movement lasted for hundreds of millions of years. When they finally met, they did not join together quietly. The edges of the continents pushed against one another with enormous force. Since the rocks could not easily move out of the way, they became folded, broken, and lifted high into the air. This process created long mountain ranges that stretched across different parts of Pangea. As the continents collided, deep cracks formed beneath the surface. Large amounts of pressure built up inside the rocks. Sometimes the rocks bent slowly, at other times they broke suddenly. When this happened, the stored energy was released as powerful vibrations that traveled through the ground. These vibrations are known as earthquakes. Earthquakes happened many times during the formation of Pangea because the crust was under constant pressure from moving tectonic plates. Some earthquakes were small and affected only a limited area. Others were much stronger and could be felt across great distances. The shaking caused rocks to split apart, cliffs to collapse, and large pieces of land to shift slightly from their previous positions. Rivers sometimes changed their paths after strong earthquakes. Lakes could also be formed when landslides blocked valleys. Deep underground, faults developed where rocks had broken and moved along large cracks. These faults remained active for long periods because the tectonic plates continued to move. The formation of mountains during the age of Pangea also changed the movement of the Earth's crust. As the mountains rose higher, they added great weight to the crust below them. The rocks beneath the mountains slowly adjusted to this extra weight. Some areas were pushed downward while nearby regions rose upward. This movement happened over very long periods of time. The changing balance of the crust created new stresses that sometimes led to additional earthquakes. Volcanoes were another important part of life on Pangea. A volcano forms when melted rock from deep inside the Earth rises toward the surface. This melted rock is called magma while it is still underground. When it reaches the surface, it is called lava. The intense heat inside the mantle melts some of the surrounding rock. The melted material then rises because it is less dense than the solid rock around it. If enough pressure builds, the magma forces its way through cracks in the crust and erupts onto the surface. Many volcanoes were active during the time of Pangea. Some stood alone while others formed long chains that stretched across wide regions. The eruptions varied greatly. Some released lava that flowed quietly across the land for many kilometers. Other eruptions were much more violent. They blasted ash, gases and broken pieces of rock high into the sky. Thick clouds of volcanic ash spread across large areas, covering forests, rivers, lakes and plains with fresh layers of fine material. Volcanic gases played an important role in the atmosphere during this period. Eruptions released water vapor, carbon dioxide, sulfur gases, and many other substances. These gases mixed with the air and sometimes changed local weather conditions. Ash falling from the sky could block sunlight for a time in nearby regions. Rain mixed with volcanic gases sometimes became more acidic than normal, affecting plants growing close to active volcanoes. Fresh lava covered older landscapes during many eruptions. As the lava cooled, it hardened into solid rock. Layer upon layer of volcanic rock built up over many eruptions. Some volcanic mountains became taller with each eruption, others collapsed after emptying large underground magma chambers. The collapse created wide depressions in the ground. Later eruptions sometimes filled these depressions with new lava flows. The movement of tectonic plates beneath Pangea did not stop after the supercontinent had formed. The plates continued to shift slowly beneath the giant landmass. Heat from the mantle remained active below the crust. As this heat moved upward, it created areas where the crust became thinner. Magma found it easier to rise through these weaker regions. New volcanoes appeared while older ones became inactive after their magma supply decreased. Some volcanic regions remained active for very long periods. Repeated eruptions produced thick layers of hardened lava that covered enormous areas. These volcanic rocks became part of the foundation of the land. Millions of years later, geologists would discover these ancient lava layers and use them to understand the history of the Earth during the age of Pangea. Earthquakes often happened near volcanic regions because both were connected to movements inside the Earth. Rising magma placed pressure on surrounding rocks. As the rocks cracked to make room for the magma, earthquakes occurred. Sometimes small earthquakes happened before an eruption. At other times they continued while lava flowed onto the surface. After eruptions ended, the ground often remained unstable because the underground rock had changed. The interior of Pangea experienced different geological conditions from those near its edges. Since the supercontinent was so large, its central regions were located far from the oceans. These inland areas often had dry climates, but geological forces continued beneath the surface. Ancient faults crossed many parts of the continent. Some remained inactive for long periods before becoming active again as tectonic stresses changed. Large mountain ranges influenced geological activity by affecting the movement of the crust. Heavy mountains slowly wore down through weathering and erosion. Wind carried away fine particles. Rivers transported sand, mud and gravel into lower areas. As the mountains lost material, the crust beneath them slowly rose again because of the reduced weight. This gradual adjustment continued for millions of years and sometimes affected nearby faults, sediments collected in valleys and low-lying regions throughout Pangea. Rivers flowing from the mountains carried broken rock into lakes, floodplains, and coastal regions. Over time, these sediments became thicker. The weight of these growing layers slowly pushed the crust downward. New rock formed as the sediments were buried deeper beneath additional layers. Heat and pressure gradually changed loose sediments into solid sedimentary rocks. Deep below the surface, older rocks experienced increasing pressure and temperature. Some changed into metamorphic rocks without completely melting. Minerals inside these rocks became arranged in new ways because of the changing conditions. These rocks provide important evidence today about the forces that acted beneath Pangea. Not every volcanic eruption reached the surface. In many places, magma cooled underground before it could erupt. This underground magma formed large bodies of igneous rock. Some remained hidden deep beneath the surface until erosion removed the rocks above them millions of years later. Today, geologists study these underground formations to understand ancient volcanic systems that existed during the time of Pangea. The crust beneath Pangea contained many different types of rocks that had formed over long periods before the supercontinent existed. As continents collided, these older rocks were squeezed, folded, and broken. Some rocks that had once been buried deep underground were later lifted toward the surface as mountains formed. Erosion then slowly exposed them, allowing their history to be preserved within the landscape. Throughout the lifetime of Pangea, geological activity never completely stopped. Heat continued to rise from the Earth's interior. Tectonic plates continued their slow movement. Volcanoes erupted at different times in different places. Earthquakes released pressure built up within the crust. Mountains continued to rise in some regions, while erosion lowered them in others. Valleys deepened, rivers changed their courses, and new rock layers formed as the Earth's surface continued to change over millions of years. Around 230 million years ago, during the later part of the Triassic period, the first true dinosaurs began to spread across the great supercontinent called Pangea. At that time, nearly all of Earth's land was joined together into one enormous landmass. There were no wide oceans separating continents as there are today. Animals could travel across long stretches of land without meeting the barriers that later formed when the continents slowly drifted apart. This connected world created many opportunities for dinosaurs to move into new places, find food, and establish populations in different environments. The earliest dinosaurs did not immediately become the most common animals on land. They lived alongside many other groups of reptiles that had already been successful for millions of years. Large amphibians still lived in rivers and lakes. Many crocodile-like reptiles walked on land instead of living mostly in water as modern crocodiles do. There were also armored reptiles, long-necked plant-eaters, and many other animals that filled different roles in nature. The first dinosaurs formed only a small part of these ecosystems. Scientists believe that the earliest dinosaurs evolved from a group of reptiles known as archosaurs. These reptiles already had several features that later became common in dinosaurs. Their legs were positioned more directly beneath their bodies instead of spreading outward. This body structure allowed more efficient walking and running. Over many generations, natural changes produced animals that gradually developed the features that identified them as the first dinosaurs. Many of these early dinosaurs were small compared to the giant dinosaurs that appeared much later. Some were only about the size of a dog, while others reached the size of a horse. Their lighter bodies allowed them to move quickly through forests, open plains, and river valleys. Speed helped them search for food, escape danger, and explore new areas across Pangea. The climate of Pangea played an important part in the spread of dinosaurs. Much of the interior of the supercontinent was dry, because moisture from the oceans could not easily reach these distant inland regions. Large deserts covered many areas. Other places experienced long dry seasons, followed by periods of heavy rain. Rivers expanded during wet seasons and became much smaller during dry periods. Plants and animals had to survive these changing conditions. Near rivers, lakes, and coastal regions, plant life was much richer. Forests of conifers, seed ferns, cycads, ginkgos, and other ancient plants provided food and shelter for many animals. Ferns and horsetails covered moist ground near streams and wetlands. These greener regions became important habitats, where many early dinosaurs lived and found enough food to survive. Small meat-eating dinosaurs hunted insects, lizards, early mammals, and other small reptiles. Some hunted alone, while others may have hunted in small groups. Although direct evidence for group hunting among the earliest dinosaurs remains limited. Their sharp teeth, strong jaws, and long legs helped them catch moving prey. Their claws allowed them to hold struggling animals while feeding. Plant-eating dinosaurs had different teeth and jaws. Their teeth were shaped for cutting or crushing tough plant material. Since many ancient plants were fibrous and difficult to digest, these dinosaurs spent much of their time feeding. Their digestive systems gradually became better at processing leaves, stems, and other plant parts. Some swallowed small stones that remained in the stomach to help grind food before digestion. As dinosaurs moved into different regions of Pangea, they encountered many different habitats. Some lived near rivers that flooded during rainy seasons. Others occupied dry plains where water became scarce for long periods. Mountain ranges, volcanic regions, forests, and coastal environments each presented different challenges. Dinosaurs that could adapt to these changing conditions were more likely to survive and leave offspring. The connected landmass of Pangea allowed dinosaur populations to spread over enormous distances. Animals could gradually move from one region to another over many generations. This movement did not happen quickly. It took countless generations for dinosaur populations to expand across such vast areas. Young animals grew, reproduced, and their descendants slowly occupied new territories. The fossils of early dinosaurs have been found on continents that are now separated by wide oceans. Fossils discovered in South America, Africa, North America, Europe, Asia, and Antarctica show that dinosaurs had already spread widely before Pangea broke apart. These discoveries help scientists understand that these continents were once joined together. Similar dinosaur fossils found in distant places provide strong evidence for the former connection of Earth's landmasses. Among the earliest known dinosaurs were small carnivores that hunted actively and plant eaters that fed on the abundant vegetation available in suitable habitats. Some species developed longer necks that helped them reach higher plants. Others remained low feeders, eating vegetation close to the ground. Different feeding habits reduced competition for the same food resources and allowed several dinosaur species to live in the same general area. During the late Triassic period, Earth experienced repeated environmental changes. Volcanic activity affected many regions of Pangea. Massive eruptions released large amounts of gases and ash into the atmosphere. These events influenced temperatures, rainfall, and the chemistry of the air and oceans. Many groups of animals struggled to survive these difficult conditions. Toward the end of the Triassic period, one of Earth's major extinction events occurred. Many reptiles that had dominated the land disappeared. Numerous marine animals also became extinct. Scientists believe that extensive volcanic eruptions associated with the opening of the Central Atlantic region played a major role in causing these environmental disturbances. As ecosystems changed, dinosaurs survived more successfully than many of their competitors. The disappearance of many competing animal groups opened ecological opportunities for dinosaurs. Habitats that had once been occupied by other reptiles became available. Food sources increased for surviving species. Dinosaur populations expanded into these newly available environments. Over time, they became the dominant large land animals across much of the world. The beginning of the Jurassic period marked an important stage in dinosaur history. the surviving dinosaur groups diversified into many new forms. Some evolved into large meat-eaters with powerful jaws and strong legs. Others became enormous plant-eaters with long necks and massive bodies. Smaller species also continued to thrive in forests, floodplains, and coastal regions. As dinosaur diversity increased, different body shapes appeared. Some species developed longer necks that allowed access to vegetation, growing at different heights. Others evolved stronger legs that supported increasing body size. Changes in skull shape, teeth, and jaws reflected different diets. These adaptations allowed dinosaurs to occupy many ecological roles across Pangea. Reproduction played a major role in dinosaur success. Like most reptiles, dinosaurs laid eggs. Females selected nesting sites where eggs could develop safely. Some species probably buried their eggs beneath sand, soil, or vegetation. Others may have built simple nests. Fossil discoveries from several dinosaur groups suggest that at least some parents remained near their nests for a period after laying eggs. Evidence from later dinosaurs also shows that some adults cared for newly hatched young. Young dinosaurs faced many dangers from the moment they hatched. Small predators hunted eggs and hatchlings. Harsh weather, flooding, drought, and lack of food also threatened survival. Only a small number of young dinosaurs likely reached adulthood. Those that survived continued the spread of their species across the connected lands of Pangea. Bones of early dinosaurs show signs of relatively rapid growth compared with many earlier reptiles. Fast growth allowed young animals to reach larger sizes more quickly, reducing their vulnerability to predators. Studies of fossil bone tissue reveal growth patterns that indicate active lives and steady development during favorable seasons. Scientists continue to study fossil footprints left by dinosaurs walking across soft mud millions of years ago. These trackways reveal information that bones alone cannot provide. They show walking speed, direction of travel, body posture, and sometimes the presence of several individuals moving together. Fossil tracks found across different continents provide additional evidence of the wide distribution of dinosaurs during the time of Pangea. Sedimentary rocks preserve not only dinosaur bones, but also fossilized plants, pollen, spores, insects, and other animals that lived beside them. By studying all these fossils together, scientists reconstruct the environments where dinosaurs lived. They examine ancient river channels, lake deposits, floodplains, forests, and desert dunes to understand how changing landscapes influenced dinosaur evolution and distribution. Although the continents remained connected, regional differences still existed across Pangea. Northern and southern regions experienced different seasonal patterns. Some areas received more rainfall than others. Volcanic mountains created local environments with unique conditions. Dinosaurs gradually adapted to these regional differences, leading to the development of new species over long periods of time. As generations passed through millions of years, dinosaur populations continued expanding across the vast supercontinent. Small evolutionary changes accumulated slowly. New species appeared while older ones disappeared. The history of dinosaurs during this period was shaped by changing climates, shifting landscapes, volcanic activity, natural selection, reproduction, migration, and the continuous movement of living populations across the connected lands of ancient Pangea. About 201 million years ago, the Jurassic period began after the end of the Triassic period. This was a time when life on Earth continued to recover and spread after the great extinction that had happened at the end of the Triassic. Many groups of animals that had survived began to grow in number and spread into new places. Among them were the dinosaurs, which became the largest land animals in many parts of the world. During this period, the great supercontinent called Pangea was no longer staying together. Deep inside the Earth, slow movements of the crust caused the land to stretch, crack, and slowly pull apart. These changes happened over millions of years. They were so slow that no living animal could notice them during its lifetime, yet over many generations they changed the shape of the planet. At the beginning of the Jurassic period, many of the land areas were still connected. Animals could move across wide regions without meeting large oceans that blocked their paths. Forests stretched across large areas, rivers crossed broad plains, and mountains stood in many regions. As the land slowly separated, new seas entered the growing gaps between the continents. These new bodies of water slowly became wider and deeper. They changed local weather, rainfall, and temperatures. They also created new coastlines where different plants and animals could live. The movement of the continents was caused by the slow motion of large pieces of the Earth's outer layer, called tectonic plates. These plates floated on hotter rock deep below the surface. Heat from inside the Earth caused the plates to move little by little. In some places the plates pushed against each other. In other places they moved away from each other. During the Jurassic period, many of the important changes happened where the plates slowly pulled apart. As they separated, cracks formed in the ground. Hot melted rock rose through these cracks and cooled into new crust. Over long periods, this process created new ocean floors. The northern part of Pangea slowly became a landmass known as Laurasia. This included areas that later became North America, Europe, and much of Asia. The southern part became Gondwana. Gondwana included land that later became South America, Africa, Antarctica, Australia, the Indian subcontinent, and Madagascar. At first, these giant landmasses were still close together, but they continued to move apart throughout the Jurassic period. The distance between them slowly increased as new ocean crust formed between them. The opening of new oceans changed many parts of the Earth. Water from the seas moved into lower areas that had once been dry land. New coastlines appeared. Shallow seas covered some regions, while other areas remained dry. Many marine animals entered these shallow waters, where sunlight reached the sea floor and supported many forms of life. Coral reefs grew in warm seas, while fish, shellfish, and many kinds of swimming reptiles lived in the surrounding waters. The climate during much of the Jurassic period was generally warm. There were no large ice sheets covering the poles as there are today. Because of this, sea levels remained high in many places. Warm air carried moisture across the land. Some regions received frequent rainfall and supported thick forests. Other places remained dry for long periods. Different climates across the separating continents allowed many kinds of plants and animals to live in areas that suited their needs. Forests became one of the most important parts of Jurassic landscapes. Flowering plants had not yet appeared. Instead, forests were made mainly of conifers, cycads, ginkgos, seed ferns, tree ferns, horsetails, mosses, and many other ancient plants. Tall conifer trees covered hills and valleys. Their seed provided food for some animals. Ferns spread across the forest floor where enough moisture was available. Thick plant growth created many hiding places for small animals and young dinosaurs. The rivers of the Jurassic carried fresh water from mountains to lowlands and eventually into the seas. Along these rivers, rich soils supported dense plant life. Floods sometimes covered wide areas with mud and sand. These floods buried dead plants and animals. Millions of years later, some of these buried remains became fossils. Today, these fossils help scientists learn about Jurassic environments plants, and animals. Dinosaurs became more successful than ever before during this period. Many groups grew larger than their ancestors. From the Triassic, some developed longer necks that allowed them to reach leaves growing high in trees. Others became faster hunters with powerful legs and sharp teeth. Their bodies showed many different shapes, depending on the food they ate and the environments where they lived. Among the largest plant-eating dinosaurs were the sauropods. These animals had very long necks, long tails, small heads, and thick legs that supported their heavy bodies. They spent much of their time feeding on leaves from tall trees and other plants. Their long necks allowed them to reach different parts of the forest without moving their whole bodies very often. Their teeth were shaped for stripping leaves from branches rather than chewing food. After swallowing the plants, food passed into their large digestive systems, where it was broken down over time. Some sauropods traveled in groups. Living together may have helped protect younger animals from large meat-eating dinosaurs. Fossil discoveries show that young sauropods were much smaller than adults. As they grew, they became less likely to be attacked because of their increasing size. Full-grown sauropods were among the largest land animals that have ever lived. One well-known Jurassic sauropod was Brachiosaurus. Its front legs were longer than its back legs, giving its body a sloping shape. It could reach leaves growing high above the ground. Another famous sauropod was Diplodocus, which had an extremely long body and tail. Apatosaurus also lived during this time and was another giant plant-eater that moved across forests and open land in search of food. Large meat-eating dinosaurs also became important members of Jurassic ecosystems. One of the best known was Allosaurus. This predator had strong legs, sharp claws, powerful jaws, and many curved teeth. It hunted other dinosaurs and probably also fed on animals that had already died. Its sharp senses helped it find food across large areas. Other meat-eating dinosaurs included Ceratosaurus, which had a horn on its nose, and Torvosaurus, another large hunter that lived in parts of Laurasia. These predators lived alongside many smaller, meat-eating dinosaurs that hunted lizards, early mammals, insects, and other small animals. Different hunters often focused on different kinds of prey, allowing several species to live in the same environment. As the continents slowly separated, populations of dinosaurs became divided by growing seas and changing landscapes. Groups that had once lived together found themselves living on different land masses. Since they could no longer easily move between these regions, they slowly changed over many generations. Small differences that appeared through natural variation were passed from parents to young. Over long periods, these differences became greater, leading to the appearance of new species adapted to local environments. Scientists study these changes by examining fossils from many different parts of the world. Fossils found in rocks of similar age often show that closely related dinosaurs lived on continents that were once connected. Later fossils reveal increasing differences as the continents continued to separate. These discoveries support the idea that continental movement played an important part in the history of dinosaur evolution. The growing oceans also affected weather patterns. Large bodies of water stored heat and released it slowly. Winds carried moisture inland, bringing rain to many regions. In some places this supported thick forests, while other regions remained more open with scattered vegetation. Dinosaurs living in these different environments developed features that helped them survive where they lived. The Cretaceous period was the last period of the age of dinosaurs. It began about 145 million years ago and lasted until about 66 million years ago. During this very long stretch of time, Earth continued to change in many ways. The continents kept moving across the surface of the planet because of the slow movement of the tectonic plates beneath them. Oceans became wider in some places, while others became smaller. Mountain ranges rose in different parts of the world. Volcanoes remained active in many regions, and earthquakes continued to shape the land. The climate also changed over time, affecting the plants, animals, rivers, forests, deserts and seas that covered Earth. At the beginning of the Cretaceous period, the giant supercontinent called Pangea had already broken apart. The land had separated into several large continents that continued to move farther away from one another. North America and Europe were slowly drifting apart as the Atlantic Ocean became wider. South America also moved away from Africa. India separated from the southern landmass and began a long journey toward Asia. Australia remained connected to Antarctica during much of the period before slowly beginning to separate. These changes happened very slowly. A person living through a lifetime would not have noticed the movement, but over millions of years the changes became enormous. The oceans played a major part in shaping the world during the Cretaceous period. Sea levels were much higher than they are today for long parts of the period. Large areas of land that are now dry were covered by shallow seas. Warm ocean water spread into the middle parts of some continents. These inland seas supported many kinds of life. Fish, sharks, marine reptiles, shellfish, and countless tiny living things filled these waters. When many of these organisms died, their remains settled onto the sea floor and slowly became layers of rock. Today, these rocks help scientists learn about the ancient oceans and the creatures that lived in them. One of the best-known inland seas stretched across much of North America. It divided the continent into two large land areas for millions of years. Along its shores lived many different animals. Rivers carried mud, sand and dead plants into the sea, creating rich environments where many species could survive. As sea levels rose and fell over long periods, the coastline moved many times, leaving behind different layers of sediment that can still be studied today. The climate during much of the Cretaceous period was generally warmer than the climate of today. There were no large ice sheets covering the North Pole or the South Pole for most of this time. Because of the warmer conditions, forests grew in many places, even at high latitudes. Some areas received heavy rainfall and supported thick forests with tall trees, ferns, mosses and many flowering plants. Other regions were much drier and contained open landscapes with fewer trees. Seasonal changes still occurred, especially in places closer to the poles where long periods of daylight and darkness affected the living things that lived there. The atmosphere also differed from today's atmosphere. Carbon dioxide levels were often higher than modern levels. This helped create warmer global temperatures. Volcanoes release gases into the atmosphere, and the oceans exchange gases with the air over millions of years. These natural processes influenced Earth's climate throughout the Cretaceous period. Scientists continue to study rocks, fossil leaves, ancient soils, and tiny fossils preserved in ocean sediments to better understand the climate of this ancient world. Plants experienced some of the greatest changes during the Cretaceous period. Earlier in Earth's history, forests had been dominated by conifers, cycads, ginkgos, ferns, and other ancient groups of plants. During the Cretaceous, flowering plants began to spread across many parts of the world. These plants are known as angiosperms. They produced flowers, seeds, protected inside fruits, and many different forms of leaves. At first, they were not very common, but over millions of years they became more widespread and more diverse. The rise of flowering plants changed many ecosystems. These plants provided new sources of food for animals. They also created new habitats where insects, birds, and small mammals could live. Their seeds and fruits became important food for many creatures. Different kinds of flowers attracted insects that carried pollen from one plant to another. This process helped flowering plants reproduce successfully and spread into many different environments. Insects became even more diverse during the Cretaceous period. Bees appeared and began visiting flowers to collect nectar and pollen. Butterflies also developed during this time. Beetles, ants, wasps, flies, dragonflies, and many other insects filled forests, grass-covered areas, wetlands, and riverbanks. Many insects formed close relationships with flowering plants. As plants changed, insects also changed, leading to the development of many new species over millions of years. The forests of the Cretaceous were home to many different animals. Dinosaurs remained the largest land animals and occupied many different environments. Some fed on plants, while others hunted other animals. There were giant dinosaurs that walked on 4 legs, smaller fast-running species, heavily armored forms, horned dinosaurs, duck-billed dinosaurs, and many kinds of meat-eating dinosaurs. Every continent that existed during the Cretaceous supported its own collection of dinosaur species, although the exact groups varied from place to place, because the continents were becoming more isolated from one another. Large plant-eating dinosaurs spent much of their time searching for food. Many lived in herds, which may have helped protect younger animals from predators. Some laid eggs in nesting grounds where many females gathered together during the breeding season. Fossils of nests, eggs, and young dinosaurs show that at least some species cared for their young after they hatched. Scientists continue to discover evidence that helps explain how these animals lived, grew, and reproduced. Meat-eating dinosaurs occupied the highest hunting positions in many land ecosystems. They had sharp teeth, strong jaws, and powerful legs. Different species hunted in different ways. Some chased prey across open ground, while others may have depended on surprise attacks in forests or near rivers. Fossils sometimes preserve bite marks on bones, giving scientists clues about hunting behavior and feeding habits. In some cases, healed injuries show that prey animals survived attacks and continued living afterward. Small dinosaurs were also common. Many had feathers covering parts of their bodies. Some used feathers mainly for warmth, display, or protecting eggs. Others may have used feathered arms to help them balance while running or climbing. Over millions of years, feathered dinosaurs became increasingly important in understanding the origin of birds. Fossils discovered in many countries show that birds evolved from small feathered dinosaurs during earlier periods and continued to diversify throughout the Cretaceous. Early birds developed many different lifestyles during the Cretaceous period. Some flew over forests while others lived near lakes, rivers, and coastlines. Their feathers allowed them to fly efficiently, although not every early bird flew in the same way as modern birds. Some still had teeth inside their beaks, while others possessed claws on their wings. As millions of years passed, many features seen in modern birds became more common. The skies were also filled with flying reptiles called pterosaurs. These animals were not dinosaurs, although they lived beside them for millions of years. Pterosaurs came in many sizes. Some were no larger than modern birds, while others had enormous wings that allowed them to glide over coastlines and inland seas. Many ate fish, while others fed on small animals or other available food sources. Their hollow bones helped reduce body weight, making flight easier. Marine reptiles continued to dominate many oceans during the Cretaceous period. Long-necked plesiosaurs swam through shallow and deep waters, searching for fish and squid. Powerful mosasaurs appeared later in the period and became some of the largest ocean predators. Ichthyosaurs, which had existed for millions of years before the Cretaceous, survived during part of this period before disappearing. Sea turtles also became more widespread, and many species adapted to life in the open ocean. The oceans supported countless other forms of life. Ammonites were among the most common marine animals. Their coiled shells are found today in rocks around the world. Different species evolved rapidly, making them useful for determining the ages of rock layers. Tiny plankton floated near the ocean surface, forming the base of many marine food chains. Coral reefs provided homes for fish, shellfish, sea stars, sea urchins, and many other organisms. Sharks continued to evolve into many forms, occupying different ecological roles within marine environments. Mammals remained relatively small during most of the Cretaceous period. Although they lived alongside dinosaurs, they usually occupied different ecological roles. Many were active at night and fed on insects, seeds, fruits, small animals, or plants. Some climbed trees while others dug burrows beneath the ground. Fossils show that mammals were already becoming more diverse than scientists once believed. Different groups developed specialized teeth, limbs, and feeding habits that prepared them for the greater expansion that would occur after the end of the Cretaceous period. The extinction of the dinosaurs was one of the most important events in the long history of Earth. It marked the end of a period that had lasted for many millions of years and changed the direction of life across the planet. For a very long time, dinosaurs had lived in many different environments. They walked across wide plains, moved through thick forests, searched for food near rivers and lakes, and lived along the edges of ancient seas. Some were very small, while others grew to enormous sizes. Some ate plants, while others hunted other animals. They existed in many different forms and had become the most successful large land animals of their time. During the last part of the Cretaceous period, Earth looked very different from the world of today. The continents were closer to their present positions, although they had not yet reached the places where they are now. Large inland seas covered parts of the land. Warm temperatures were common across much of the planet. Forests, flowering plants, ferns, and many other kinds of vegetation covered large areas. Insects were plentiful, and birds had become more common. Mammals also lived during this time, although they were still mostly small animals that stayed away from the larger dinosaurs. The oceans were filled with many different forms of life. Large marine reptiles hunted in the seas, while fish, sharks, shellfish, and many tiny sea creatures lived in great numbers. Coral reefs supported many kinds of animals, and microscopic organisms floated near the surface of the water. These tiny forms of life played an important part in the food chain because many larger animals depended on them for food, either directly or indirectly. Life on land was also rich and varied. Huge plant-eating dinosaurs wandered across open areas where food was plentiful. Meat-eating dinosaurs searched for prey in forests and plains. Smaller dinosaurs lived among thick plants, where they could find insects, seeds, fruits, or small animals. Different species filled different roles in nature. This wide variety of life had developed over many millions of years through slow changes that allowed animals and plants to adapt to their surroundings. Scientists have spent many years studying the extinction of the dinosaurs. They have collected fossils from every continent where dinosaur remains have been found. They have examined layers of rock that were formed during the end of the Cretaceous period. These rocks preserve evidence of the conditions that existed before, during, and after the extinction. Each fossil and each layer of rock adds another piece to the story. One of the strongest pieces of evidence points to the impact of a very large asteroid. This asteroid was a rocky object that travelled through space around the Sun. For a long time, it moved silently through the solar system until its path crossed that of Earth. When it entered Earth's atmosphere, it was travelling at an extremely high speed. The object did not slow down enough to prevent a collision. Instead, it struck the planet with enormous force. Scientists believe this impact happened about 66 million years ago. The asteroid hit an area that is now part of the Yucatan Peninsula in present-day Mexico. The collision released an amount of energy far greater than any natural disaster experienced by human civilization. Within moments, the surface of Earth near the impact site changed completely. The asteroid created an enormous crater. Today, this crater is known as the Chicxulub crater. Although much of it is buried beneath younger rocks and sediments, scientists have mapped its size using modern equipment. The crater stretches across a very large area and provides clear evidence that an object from space struck Earth at the end of the Cretaceous period. The force of the impact shattered rocks deep beneath the ground. Huge amounts of dust, ash, and broken rock were blasted high into the atmosphere. Molten rock was thrown into the sky, where it cooled before falling back toward Earth's surface. Many of these pieces became tiny glass-like particles that are still found in rocks formed during that time. The impact also produced powerful shock waves that spread across the surrounding land. Earthquakes shook large regions. The ground cracked and landslides occurred in many places. The force of the collision disturbed both land and sea over a vast distance. The asteroid struck near the ocean, causing massive waves to spread outward in every direction. These waves travelled across ancient seas and flooded coastal regions. Sediments were carried far from their original locations, leaving clear signs in the rocks that scientists study today. Some areas were buried beneath thick layers of debris carried by the water. As material from the impact returned to Earth's surface, it produced intense heat in many places. Forests and grasslands caught fire over wide areas. Smoke from these fires mixed with dust already filling the atmosphere. Large amounts of soot rose into the sky and remained there for a long time. One of the greatest effects of the impact was the enormous cloud of dust and tiny particles that spread around the entire planet. These particles blocked much of the sunlight that normally reached Earth's surface. Days became much darker than usual. Plants received far less light, making it difficult for them to carry out photosynthesis. Without enough sunlight, many plants stopped growing and eventually died. The loss of plant life quickly affected plant-eating animals. Dinosaurs that depended on leaves, branches, flowers, fruits, or other vegetation found less and less food. Young plants failed to replace older ones and forests began to change. Many areas that had once supported large herds of plant-eating dinosaurs could no longer provide enough food. As plant-eating dinosaurs disappeared, meat-eating dinosaurs also faced serious problems. Their prey became scarce. Even powerful hunters could not survive when food became difficult to find. Starvation affected many different species. Populations became smaller as more animals died than were born. The effects of the impact did not end after only a few days or weeks. Scientists believed that the dust remained in the atmosphere for many months, and possibly even longer. During this time, the climate changed rapidly. Temperatures dropped because much less sunlight reached the ground. Many regions experienced conditions that were very different from those that had existed before the impact. Cold temperatures placed additional stress on animals and plants already struggling to survive. Many species had evolved under warm conditions and were not able to adapt quickly enough. Eggs, young animals, and delicate plants were especially vulnerable. Rainfall patterns also changed. Some places became much drier, while others experienced unusual weather. Rivers and lakes changed as water levels rose or fell. Wetlands that had supported many forms of life were affected. These environmental changes made survival even more difficult. For countless species, the oceans also experienced major changes. Tiny organisms living near the surface depended on sunlight for photosynthesis. As sunlight became weaker, many of these microscopic organisms died. Their disappearance affected fish and other sea animals that depended on them for food. The effects spread through the food chain, from the smallest organisms to the largest predators. Chemical changes took place in the atmosphere as well. Gases released by the impact and by widespread fires mixed with the air. Some scientists believe that acid rain developed in many regions. This rain may have damaged plants, polluted freshwater habitats, and affected animals living both on land and in water. Scientists continue to examine evidence preserved in rocks around the world. One important clue is a thin layer of clay found in many places that formed at the time of the extinction. This layer contains unusually high amounts of the element iridium. On Earth's surface, iridium is uncommon, but it is found in greater amounts inside many asteroids. The discovery of this iridium-rich layer provided strong evidence that an asteroid impact had occurred. Researchers have also found tiny shocked quartz crystals in rocks from the same period. These crystals contain special patterns formed only under extremely high pressure. Such pressure can occur during a massive asteroid impact. Their presence supports the idea that Earth experienced an enormous collision at the end of the Cretaceous period. Another important discovery has been the presence of tiny glass spheres called tektites and other melted rock particles. These formed when rocks were heated to very high temperatures during the impact. They cooled as they traveled through the atmosphere before falling back to the ground. Similar materials have been found in many places around the world, showing how far the debris spread. Although the asteroid impact is considered the main cause of the extinction, many scientists also study other events that may have added to the environmental changes. During the same general period, huge volcanic eruptions were taking place in what is now India. These eruptions produced enormous amounts of lava over a very long time. The lava spread across large areas, forming thick layers of volcanic rock that remain visible today. The extinction of the dinosaurs was one of the most important events in the long history of Earth. It marked the end of a period that had lasted for many millions of years and changed the direction of life across the planet. For a very long time, dinosaurs had lived in many different environments. They walked across wide plains, moved through thick forests, searched for food near rivers and lakes, and lived along the edges of ancient seas. Some were very small, while others grew to enormous sizes. Some ate plants, while others hunted other animals. They existed in many different forms and had become the most successful large land animals of their time. During the last part of the Cretaceous period, Earth looked very different from the world of today. The continents were closer to their present positions, although they had not yet reached the places where they are now. Large inland seas covered parts of the land. Warm temperatures were common across much of the planet. Forests, flowering plants, ferns, and many other kinds of vegetation covered large areas. Insects were plentiful and birds had become more common. Mammals also lived during this time, although they were still mostly small animals that stayed away from the larger dinosaurs. The oceans were filled with many different forms of life. Large marine reptiles hunted in the seas, while fish, sharks, shellfish, and many tiny sea creatures lived in great numbers. Coral reefs supported many kinds of animals, and microscopic organisms floated near the surface of the water. These tiny forms of life played an important part in the food chain because many larger animals depended on them for food, either directly or indirectly. Life on land was also rich and varied. Huge plant-eating dinosaurs wandered across open areas where food was plentiful. Meat-eating dinosaurs searched for prey in forests and plains. Smaller dinosaurs lived among thick plants, where they could find insects, seeds, fruits, or small animals. Different species filled different roles in nature. This wide variety of life had developed over many millions of years, through slow changes that allowed animals and plants to adapt to their surroundings. Scientists have spent many years studying the extinction of the dinosaurs. They have collected fossils from every continent where dinosaur remains have been found. They have examined layers of rock that were formed during the end of the Cretaceous period. These rocks preserve evidence of the conditions that existed before, during, and after the extinction. Each fossil and each layer of rock adds another piece to the story. One of the strongest pieces of evidence points to the impact of a very large asteroid. This asteroid was a rocky object that travelled through space around the Sun. For a long time it moved silently through the solar system until its path crossed that of Earth. When it entered Earth's atmosphere, it was travelling at an extremely high speed. The object did not slow down enough to prevent a collision. Instead, it struck the planet with enormous force. Scientists believe this impact happened about 66 million years ago. The asteroid hit an area that is now part of the Yucatan Peninsula in present-day Mexico. The collision released an amount of energy far greater than any natural disaster experienced by human civilization. Within moments, the surface of Earth near the impact site changed completely. The asteroid created an enormous crater. Today, this crater is known as the Chicxulub crater. Although much of it is buried beneath younger rocks and sediments, scientists have mapped its size using modern equipment. The crater stretches across a very large area and provides clear evidence that an object from space struck Earth at the end of the Cretaceous period. The force of the impact shattered rocks deep beneath the ground. Huge amounts of dust, ash and broken rock were blasted high into the atmosphere. Molten rock was thrown into the sky, where it cooled before falling back toward Earth's surface. Many of these pieces became tiny glass-like particles that are still found in rocks formed during that time. The impact also produced powerful shock waves that spread across the surrounding land. Earthquakes shook large regions. The ground cracked and landslides occurred in many places. The force of the collision disturbed both land and sea over a vast distance. The asteroid struck near the ocean, causing massive waves to spread outward in every direction. These waves travelled across ancient seas and flooded coastal regions. Sediments were carried far from their original locations, leaving clear signs in the rocks that scientists study today. Some areas were buried beneath thick layers of debris carried by the water. As material from the impact returned to Earth's surface, it produced intense heat in many places. Forests and grasslands caught fire over wide areas. Smoke from these fires mixed with dust already filling the atmosphere. Large amounts of soot rose into the sky and remained there for a long time. One of the greatest effects of the impact was the enormous cloud of dust and tiny particles that spread around the entire planet. These particles blocked much of the sunlight that normally reached Earth's surface. Days became much darker than usual. Plants received far less light, making it difficult for them to carry out photosynthesis. Without enough sunlight, many plants stopped growing and eventually died. The loss of plant life quickly affected plant-eating animals. Dinosaurs that depended on leaves, branches, flowers, fruits, or other vegetation found less and less food. Young plants failed to replace older ones and forests began to change. Many areas that had once supported large herds of plant-eating dinosaurs could no longer provide enough food. As plant-eating dinosaurs disappeared, meat-eating dinosaurs also faced serious problems. Their prey became scarce. Even powerful hunters could not survive when food became difficult to find. Starvation affected many different species. Populations became smaller as more animals died than were born. The effects of the impact did not end after only a few days or weeks. Scientists believe that the dust remained in the atmosphere for many months, and possibly even longer. During this time, the climate changed rapidly. Temperatures dropped because much less sunlight reached the ground. Many regions experienced conditions that were very different from those that had existed before the impact. Cold temperatures placed additional stress on animals and plants already struggling to survive. Many species had evolved under warm conditions and were not able to adapt quickly enough. Eggs, young animals, and delicate plants were especially vulnerable. Rainfall patterns also changed. Some places became much drier, while others experienced unusual weather. Rivers and lakes changed as water levels rose or fell. Wetlands that had supported many forms of life were affected. These environmental changes made survival even more difficult for countless species. The oceans also experienced major changes. Tiny organisms living near the surface depended on sunlight for photosynthesis. As sunlight became weaker, many of these microscopic organisms died. Their disappearance affected fish and other sea animals that depended on them for food. The effects spread through the food chain, from the smallest organisms to the largest predators. Chemical changes took place in the atmosphere as well. Gases released by the impact and by widespread fires mixed with the air. Some scientists believe that acid rain developed in many regions. This rain may have damaged plants, polluted freshwater habitats, and affected animals living both on land and in water. Scientists continue to examine evidence preserved in rocks around the world. One important clue is a thin layer of clay found in many places that formed at the time of the extinction. This layer contains unusually high amounts of the element iridium. On Earth's surface, iridium is uncommon, but it is found in greater amounts inside many asteroids. The discovery of this iridium-rich layer provided strong evidence that an asteroid impact had occurred. Researchers have also found tiny shocked quartz crystals in rocks from the same period. These crystals contain special patterns formed only under extremely high pressure. Such pressure can occur during a massive asteroid impact. Their presence supports the idea that Earth experienced an enormous collision at the end of the Cretaceous period. Another important discovery has been the presence of tiny glass spheres called tektites and other melted rock particles. These formed when rocks were heated to very high temperatures during the impact. They cooled as they traveled through the atmosphere before falling back to the ground. Similar materials have been found in many places around the world, showing how far the debris spread. Although the asteroid impact is considered the main cause of the extinction, many scientists also study other events that may have added to the environmental changes. During the same general period, huge volcanic eruptions were taking place in what is now India. These eruptions produced enormous amounts of lava over a very long time. The lava spread across large areas, forming thick layers of volcanic rock that remain visible today.